If you see a 2026th derivative, it looks computationally intensive. Direct calculation is not the right approach. This appears difficult, but we will not use standard algebraic expansion. We will find a simplification. The quotient rule is the standard method, but it is inefficient here. We will not use it. Observe the complexity. By the third derivative, the expression becomes unmanageable. Direct differentiation is inefficient. Stop! We should not perform unnecessary calculations. We will find the structure that simplifies the problem. Look at the denominator. It's just x squared minus x. Factoring the denominator simplifies the problem. The expression becomes manageable. This is called decomposition. We convert this single complex fraction into two simpler ones. We have the factored form. Now we use the heaviside cover-up to split it efficiently. We separate this into two distinct terms. Now we just need the constants for the top. The shortcut is the heaviside cover-up. Oliver Heaviside was a self-taught engineer who preferred efficiency. He invented this to avoid long calculations. To find the number over x minus 1, go back to the original fraction and remove that term from the expression. What makes the hidden part 0? 1. Plug that into what's left. 1 over 1 is 1. That's A. Same thing for B. It's sitting over x, so cover the x. The root here is 0. 1 divided by 0 minus 1 is negative 1. That's B. No systems of equations are required. Substitute the values. We converted the complex fraction into two simple terms. We have decomposed the fraction. Now finding the 2026th derivative is feasible. We will use the pattern. A 2026th derivative? This seems like a difficult task. But we aren't doing manual calculation. We're looking for the pattern. Let's strip it down to x inverse first. First derivative, we just get negative 1 times x to the minus 2. Second time, that negative 2 drops down, making it positive 2 factorial. Third time, negative 3 factorial. The pattern becomes obvious now. It is systematic. It oscillates signs and builds a factorial without any complex quotient rules. Just clean, predictable logic. Now, bring back the original function. It consists of two of these terms combined. Most people see a 2026 factorial and expect difficulty. Don't. We're going to use a method that simplifies this expression significantly. Plug in 2026 for n and 2 for x. It looks complex, but the arithmetic is straightforward. 2 minus 1 is just 1, and 1 to any power is 1. This first fraction essentially evaluates to 1 and simplifies. Now we evaluate this modulo 2027. This is where we leave calculus behind and use number theory. Here is the critical observation. 2027 is a prime number. That is our indication to use Wilson's theorem. The theorem says that p minus 1 factorial is always congruent to negative 1 modulo p. Since 2026 is exactly p minus 1, we can replace that large factorial with negative 1. This is much cleaner. We only have one more term to handle before we reach the final answer. We are left with this. The only thing remaining is that fractional power of 2. 2 to the power of p inside a mod is a clear indication. Don't calculate it. Use number theory. Since our value p is prime, we can use Fermat's little theorem. Fermat proves that 2 to the p minus 1 is congruent to 1. It is a standard shortcut. Multiply by 2, and 2 to the p becomes a simple 2. The exponent is gone. Now we handle the fraction. Decimals don't exist here. We need a modular inverse. We want a number that, when doubled, is exactly one step past a multiple of 2027. 2027 is odd. Add 1 to get 2028. Divide by 2, and we get 1014. That is our modular half. Substitute it back in. The negatives cancel, and the final result is 1013. Simple. Efficiency is better than direct calculation every time. If you want math that is clear and rigorous, subscribe. See you in the next one.